Who knows what proxemics is? Okay, you read the abstract, right? Who would like to know? So, I'll let Yi tell you what proxemics is. Anyway, so Yi was an intern working with myself and Anita this summer. I don't know where Anita went. There you go. And we had a lot of fun. It was just really fun working with Yi. I had a great time. He did a great job. And I'll let him tell you what this is about.
Okay. Thank you, Simon. Glad everyone to attend my talk. So my talk is a computer vision talk. The topic is proxemic recognition. So you may wonder what is proxemics, and let's do it. So proxemics, the term is first introduced by anthropologist Edward Hall in his 1963 paper when he studied the spatial arrangements of people as they interact. So you may think that in our daily life, when there are multiple people interacting with each other in roughly same space, then proxemics happen. For example, right now, we're having a proxemics here. I will tell you what it is later. So, so in his study, he defined 4 different types of spaces. Well, from our own person point of view, you have a question? Okay. All right, let's. So from our own person point of view, the farthest space is called the public space, where you imagine that you're standing wild and the other people are all very far away from you. So there won't be any possible direct communication from you to them. And when other people come closer to you, then it turns out to be a social space where you can build a social relationship with them now. So you may think that right now, everybody is in a social space, where everybody is keeping some kind of distance there. So we can talk to each other, but we may not be able to touch. But actually, I'm wrong, sorry. I think we're in the personal space, okay. We're in the personal space, definitely. So we can touch each other by our hands. But we can speak to each other very fluently. So, but we are not in the intimate space, not the social space. I think the pairwise, everybody is in the personal space. I'm pretty confident about it now. So finally, in the intimate space, it is very obvious that if 2 persons are very, very, very close to each other, normally that means they have a very, very good relationship, like best friends or mom and baby or husband and wife. So here I show friends walk side by side with their shoulders very close to each other. So this is the intimate space. This is a very small area. And in our summer project, what we focused a lot is on this personal space and intimate space, where there are many, many interesting interactions happen there. And we want to understand and we want to study what's going on there. So here in the slides, I show 4 of the examples in these 2 spaces. The first one is the holding hands, which you can see from the top left. Then the second one is the friends walking side by side, as I already mentioned. Then the third one is the mom holding a baby. You can see they are very close because they are in a very, very good relationship. Then finally, this one is kind of complicated, but the husband is hugging his wife and also holding his hands with his wife, right? So these are very kind of interesting images, and we really want to understand what's happening there. And according to the anthropologist Edward Hall I mentioned, what he did is he found that using a small set of unit elements, call it touch codes, it can be used to represent all of these complicated interactions. So the touch codes, for example, here we have hand touch hand, shoulder touch shoulder, hand touch shoulder, arm touch torso. There may be more, but I just list 4. And can I finish this? And okay. And from the top right, we can use shoulder touch shoulder to somehow to define this image. And the bottom one, we can use the combination of hand touch hand and hand touch shoulder to represent this image. So the set may be small, but the combination could be exponentially large. That's the key idea. Yeah.
Just a clarifying question. Are you only interested in non-aggressive because in my personal state, hand-touching hand may be an aggressive, hand-touching neck may be an aggressive. I don't know. I'm asking. Is that true or not?
So
You're only considering images of peace and love and understanding, or you're considering aggressive images, or where there is an interaction, but the interaction is not on the same page?
yeah, we consider the interactions with that are not in the same age as the age, right? No.
Arresting me.
Oh yeah.
But he's touching my hand.
I see. I see. Good point. So in our data set, we indeed have a few images, but what we consider here are more like a very nice relationship. Yeah. Okay. All right. So once we are able to understand the human interactions in images, there could be a potential group of applications that have the human interactions involved there, right? I'm gonna skip these interactions.
Your question, right? We're more interested in like people, personal photos. We're not the surveillance setting. I don't know.
Oh, the Kinect setting is one in which we want to. But I understand. I just wanted to find the clarifying. Not looking for
Maybe
justification.
some of the techniques could be fun.
Okay. Then in order to study this problem, we collect a data set with 200 training images and 150 testing images collected from Simon's personal photo album. You know, imagine there cannot be any dangerous thing happen there. And also we download a pretty bunch of images from Bing Image and Google Images, also from Getty Images, a really large amount from there. And finally, Flickr. One big point we need to make is there is no video data, and we don't get any help from Kinect. So this is pure image pixel input, and our method is based on that. So here's the illustration of our proxemic dataset. The x-axis, you can imagine this represents the number of people in one image. The y-axis is the complexity I defined by myself. You may have a different opinion, but imagine that the higher, the more complex in the image. So you can see that in our data set, we have kind of a big variety from 2 people to 6 people, from people far away from each other, this social space, to people very close to each other, this intimate space. And from the simple touch code, this hand touch hand only, to the very complicated combination of touch codes, like shoulder touch shoulder, hand touch shoulder together, and whatever. So this could be very, very complicated, and you think about what would be the best way to solve this problem. So let's use the 2 boys hand touch hand as an example. What I would say is suppose we have a Kinect that can work very well on images, not the 3D depth data. And that Kinect can report us the very nice locations of the human joints. Then I guess would be, if you think, at least I think it would be the simplest way is I use the reported hand locations of the Kinect, and I compute the distances between the 2 boys' hands. And I find, the distance, this distance is so small, so I'm pretty sure that they are holding hands, right? I guess that's one of the very straightforward way. And we indeed try that. But we don't have a Kinect. So what we did is we use the input image and we extract the edge features, very discriminative image features, and we apply the current state-of-the-art pose estimation algorithms, get the human pose and get their skeletons and their joint locations by using this method. And then by using the predicted location, we finally decided whether They are hand touch hand. Sorry?
What are the features?
This feature is called histogram of oriented gradients, or HOG feature, which is right now very commonly used in computer vision field. But basically, it's the edge features. It computes the how contrast the nearby images. And we indeed did that, and we look at our experimental results on this naive approach. For here, we show the precision recall curves for hand touch hand, recognizing hand touch hand and hand touch shoulder. And we are very disappointed. So this algorithm almost works as bad as a random guess. So now we would think why this is so bad, right? So we come back to and look at the post-estimation algorithm. We would hope that, yes, of course it's bad because it cannot work as good as Kinect. So we look at it, and what we find some kind of phenomenon is that when the people in the images are not interacting with each other, I mean, when they are kind of single and there is no interruption, the post-estimation actually works not that bad. However, when there are interactions there, then, oh my God. So the post-estimation, it fails a lot. Here, they are actually very nice images I show. There are many other bad images. But what you can see is here this big occlusion because of the people overlapping, and this ambiguous parts because the post-estimation is supposed to reason whether this arm belongs to this person or that person. But our current post-estimation algorithm, it just reason about the pose independently. So it does not have that power. So you can see that it puts the same arm on the same roughly image locations, and the same predicted arm on the same roughly image locations, and it cannot handle occlusion. So that's one of the biggest reasons that this post-estimation fails. So our next step would be solve it, right? Solve the occlusion and the ambiguous parts. However, solving this problem tends to be very expensive if you want to explicitly reason about these problems. And what we did in this internship is we skip this post-estimation and directly go to the proxemic recognition. So now let me introduce our approach. So the name is called direct proxemic recognition. And similarly, given an input image with its image features extracted, as I mentioned again, we don't have any post-estimation, but just go to the hand-touch-hand or whatever interactions and decide whether they are interact. And to explain our model, we have to first trace back to the famous pictorial structure model in the computer vision literature for detecting human. So in the pictorial structure model, the human is represented with a collection of parts like head, torso, arms, and legs. And in the pictorial structure model, a scoring function is defined with respect to putting the location of parts in the image, where we write the location of part I as Li. And the score is computed using two sums, a summation over two terms. So the first term scores the unary score that put in by placing templates over some image locations. So phi would be the edge features we extracted, and alpha I are the part templates. While the second term consists of the deformation term that models the location, the pairwise location relationships between the two parts. We don't want the parts to place anywhere in the image. We want them to have consistent relative locations. And the psi are the relative location features, and beta is the model parameters favors certain certain offsets. And our model, this direct proxemic model, we give it a nickname. We call it the two-head monster model. Okay, monster. Yeah, so the extension, it's an extension of the previous model, that instead of modeling one person, we have two persons in our model. And for the hand-touch-hand, let's use that as example, we have one more springs, one more pairwise springs that connect the two hands between the two persons, making sure that they are indeed hand-touch-hand. The mathematical formulation would be almost exactly the same, but it's just we have one more person and one more spring. And because we know that in order to recognize hand-touch-hand, the legs are non-informative and the other hand could also be non-informative, so we crop it. And finally, this is our hand-touch-hand model. Yeah, go ahead.
In your pictures, all the positions are very frontal. So what happens if
Yeah. So yeah, this is another, yes, you're right. In our dataset, most of the images are frontal view person. For the side view person, so it would be, you may think that first, when we compare the baseline, we would think the baseline could also solve the side view person.
No.
But normally it didn't.
So would this work?
Yes, actually this would work because it really didn't consider too much other variety of various noises, but just focus on the particular parts. So in our model, we build in our experiments, we build 4 touch code models. One is the hand-touch-hand, one is the hand-touch-shoulder, shoulder-touch-shoulder, and finally, arm-touch-torso. We tried all these 4 models. Oh, by the way, so the inference for this model would be just by applying dynamic programming, and it can work pretty efficient. And to learn the model parameters, the SVM solver, a structural SVM solver can be used. Of course, this is not the whole story, because consider about the symmetry that the left hand touch right hand would look pretty different from the right hand touch left hand. So indeed, in the hand touch hand model, we build 4 subcategories and we combine them together. Of course, not all proxemics could happen simultaneously in one image for 2 persons. For example, if I'm touching a person's shoulder with my right hand, then I cannot touch his torso or his hand with my right hand again. Or maybe, okay. So we consider about this information too in my model. So finally, let's get to our experiments. Again, this is a naive approach, which almost works as bad as baseline. And here are our precision recall curves. Much better, although not perfect. And we also look at the comparison results quantitatively for all 4 models, and we have average 30% average precision boosting by using this direct model. Also, by using this direct proxemic model, it actually helps the pose estimation reversely in those images that this proxemics happen there. For example, here I show the comparison between applying the pose estimation and by applying our direct model. So these are all hand-touching hand images. Given the information that we know there are 2 persons that hand-touch hand, and so their hands must be close by, must be near to each other, we are able to get much better accuracy compared with the previous naive approach. And that previous naive approach cannot handle the occlusion. So similarly, for the hugging or for the hand-touch shoulder case, this scenario seems more natural. That in the pose estimation, it have to put its arm somewhere, so it follows some kind of this vertical edge shape for the arm. But our model, because we know that the hand must be very close to the shoulder, so somehow we have the power to even reason about the locations of the occluded parts. And finally, the holding baby, this hand-touch torso. Again, so this, for pose estimation only, it could be very it could be a very complicated problem because there are huge occlusion there. But once we only look at these interesting parts that are related with this hand-touch shoulder, then it really just do kind of better estimation on that particular parts. In conclusion, so we introduced a novel term in computer vision, which is called proxemics, and touch codes to model the human interactions and their spatial relationships as they interact. We develop a directly recognizing proxemic model that significantly outperforms the naive approach. And reversely, this direct proxemic model actually really do better work on post-estimation on those proxemic images than the pure post-estimation model. And I would thank Simon and MSR for giving me this great internship opportunity. I would thank Anita for a lot of very nice suggestions and help in my both research and career. I would thank Anab, I'm not sure if he's here. Oh, he's there, for letting me know the Getty images. Before that, I don't know the Getty images. I download a lot of images from there. Thank you. And I would thank Elliot for her beautiful smiling that makes our lab with sunshine every day. And finally, I would thank everybody not falling asleep in my talk. Thank you very much. Yeah. Right. Okay. Very good point. So you may think there are two ways. So one way is that I apply some kind of human detection first, get roughly the number of person and roughly their locations, then applying this kind of method to. So that's like assuming that we know the number of persons and we somehow know a roughly location. Another thing is that what we find is in the post estimation, or even this problem that we know there's not a big requirement for knowing them before. It's more like a detection problem that we are putting parts and putting these relative locations into the image and fit it best. So somehow the best scores for the fitted detections, they are really just the human touching. So it could be that beforehand we don't really need to know how many people in the image. Sure.
A really simple way is just do face detection.
Yeah.
Which sort of essentially works. And sort of the first week, I remember showing you the internal face detector.
Right.
And you just the eyes went like, wow,
yeah.
It works. That's sort of one of those sort of in industry these things get engineered well in the academic world
Right. So actually, what we did in our experiments are we really rely on this face detection. So we first get the face of the people, we know the head, roughly head location, then we compute all the other parts, the location. Oh, okay. So for this image, the dotted line means the person is in a passive mode. So the interaction, not all of them are symmetric interaction. Most of them are there's an active person, there's a passive person. When we define this person holding another person, then we know that the first person is the active one. And I use the solid line to represent the parts.
Active and passive is part of your model as well?
Yeah, it's also built in my model. Yeah. Yes. So let me ask, so do you mean like I have only the Kinect data or I have the Kinect data plus the images? Just the Kinect 3D. I would still think it would do better than using the images, but maybe the algorithm could be a little different as current Kinect using a really different algorithm than the state-of-the-art post-estimation in images. But I would think that would be very, very useful, and I believe that in the future, Kinect would have some kind of application that have the human interactions there and do some work there.
So I guess that was sort of the question in the other direction. Is there anything here that there's an opportunity to feed back into Connect?
Yeah, I think so. I think that, I mean, I think there is. It's not a here, take this piece of code and just
No, of course
right.
not.
But there's some of the ideas.
Some of these ideas, it seems to me,
Right.
might be useful in making Connect recognition more robust.
Right. And sort of, the Connect SDK is you get the skeleton out, right? And the game developers getting that. And they're generalizing that, right? But one of the points here is sort of going through the skeleton isn't always the right thing to do, right? And this is so well known in a lot of fields, right? But sort of almost jump right to the answer and just tell me, kind of hypothesize that they're holding hands and then look for that. So now maybe you could build an SDK where it's like, yeah, there's some subset of interactions that more reliably than it is. And it's using some of the, instead of having this sort of, I mean, it's possible you can just use the same algorithm, the same decision tree algorithms to just train it.
Other questions? Thanks again.
Thank you.